Welcome to episode 4 of this video series on variance of a random variable. So in the previous video, we discussed what is the formula for variance, what is the difference between getting the samples from the population data or a subset of population data. We also discussed about biased and unbiased estimators, and we also briefly discussed how calculating or measuring variance using the deviations from the sample mean and dividing it by n, that is the number of samples, could be a biased estimator. And in this video, we'll check how do we say so, why do we say so that while calculating or measuring the variance, if we calculate the deviations from the sample mean and divided by n is going to be a bias estimator, and how can we correct that using Bessel's correction. So let's get into that. So we know that variance is the expected square deviation from the mean. Now the question arises, like, which mean should we be considering? Should it be the sample mean or should it be the population mean? So let's say, for example, we have a distribution. The sample population mean is looking something like this, and x bar is the sample mean. And if we have a sample distribution looking something like this, and if we, let's say, this green part is somewhere in between the sample mean and the population mean, we can see, and we discussed that we actually wanted to calculate the deviations from the mean. Now we know that we can see that in this case, towards the left-hand side of this green part, all the samples that are there are going to be closer to the sample mean, and all the samples that are going to be lying here are going to be closer to the population mean. So if we calculate the deviation for all these points from x bar, that is the sample mean, it's going to be always less than if we are calculating deviations for all these points from mu. And the same is the case for these points where all these points are closer to mu. And if we calculate the deviations for these points with x bar, they are going to be more than the deviations when calculated from mu. So we can see, we can write it in a form that x bar square is going to be less than xi from mu, and this is the case for all the points that are actually somewhere here. So we can see that all these points are going to be underestimating the deviation, and all these points are going to be overestimating the deviation. But what is actually going to happen is it going to be underestimating or overestimating? So we can see that because the sample distribution is somewhere here, all the points or most of the points are going to be in this region. So it means that we are mostly going to be underestimating the deviations as compared to when we are calculating the deviations from the sample mean or from the population mean. We can see it from this example as well. So let's say if we are calculating the deviations from this green dot, that is the sample mean, and if we are calculating the deviation, let's say from these points, it's going to be more. What we can also show in this case, so now we have come to the conclusion that calculating deviations from sample mean is going to be underestimating the deviations. How else we can show that? So let's take another example. Let's take some samples. Let's say list of numbers from 1 to 10. Let's consider these as our samples. And let's calculate the mean for these. The very first step is let's calculate the mean. And another thing that we are probably going to be doing is, let's say, for example, instead of calculating the deviation from the sample mean, or let's say from the population mean, let's randomly pick any number and calculate the deviation of all the sample points from that number. And whatever is the sum of square deviation, let's just note it down or plot it somewhere here. And another, let's take another number and calculate the sum of square deviations. Let's take another number and just keep on calculating the deviations from some random points. So for this thing, what we have done is, let's say we are having some possible numbers, let's say from 1 to 10 with a step size of 0.1. So 1, 1.1, 1.2, 1.3, 1.4, and so on till 10. So what we are going to be doing is we are going to calculate the deviations for all these numbers from 1, and then from 1.1, from 1.2, and 1.3, and so on. So we'll be calculating the deviations for all the points, like summation of all the points, summation of the deviation of all the points from 1 and then from 1.1, and whatever is the value, we are going to be just again having it in the list. So this one is going to be somewhere here, and we are again going to be having a list of all these square deviations from each of these following numbers. What we can do is we can either plot them or just simply connect them in a list. So this is what this particular code is also doing. So we first are having some list of possible candidates, mean candidates rather. So we're just taking from 1 to n plus 1, that is 1 to 10, step size of 0.1. This is the same thing here. And then we have this function that is calculating the sum of square deviation. So it is sum of square differences. So we are taking all the numbers, that is these, and then we'll pass in any one single number, that is either 1 or 1.1. So that goes in here, and we'll be simply calculating the squared differences and we'll summing them up. This part is doing nothing but running a for. It's equivalent to running a for loop over this function. So instead of taking just one single element from this list, we have to actually run a loop over all these elements and calculate deviations for all these numbers in this list. So this is nothing but doing a vectorized map over this list. So instead of passing just one single value, we can pass the whole bunch of these numbers at once into this. So this is a vectorized function, and then we can just use this vectorized function and pass all the possible mean candidates here, and that way we'll get a list of deviations directly. So this is again the list, and what we are going to do finally is we will be calculating the mean, the minimum value for these deviations. So for which of these possible numbers the deviation was the minimum. So basically, what was the, so if this is the point, like, and we're calculating deviations, is it minimum for this point, or is it minimum for this point, or is it minimum for this point, and so on. So if you notice here, so when we are calculating the mean turns out to be 5.5, and the candidate that minimizes the sum of square differences is also 5.5. So basically, there is going to be some number here that is 5.5 that is going to minimize the sum of square deviation. How else we can do that? So let's see that this sum of square deviation, let's call it as a function of f of m being any number in this list. So this f of m is nothing but the sum of square deviation that can be written like this, and this is what we are defining somewhere here. And then what do we actually want to calculate is find the value m for which f of m is minimum. Or we can also say that find m for which the derivative of m with respect to m is equal to 0. How we can do that? We can have this function that is f of m here, the sum of square deviation, and we can calculate the derivative. That this function will calculate the derivative or the gradient for this function, and then we can pass in all the possible values that were there in the list, like put in all the values here, so that we can find for which particular m the value is actually the derivative is actually equal to 0. So we'll get the values here, and we are checking if it is, we are not exactly checking 0, but we are checking if, because there could be some precision errors, we are simply checking for which particular m the value is very close to 0. And if we see here, we find that the mean candidate where the gradient is very close to 0 is again 5.5, and this is again equal to the sampled mean that was there. So what information are we getting from this? We also again had this plot, so this is another way of doing that. So when we plotted all the square deviations with respect to m, we got this curve. And if we zoom in a little bit here, we find that the minimum value again is at 5.5, and the value turns out to be 82.5. So what we can infer from these three experiments is the sum of square deviation is minimum for x bar. So for all the values out of all the values that we selected, the sum of square deviation is minimum for the sampled mean. It means that for any other value, the sum of square deviation would be more than whatever we are getting from for this sample mean. And if we consider the other value as mu, that is the population mean, it means that the square deviation when calculated from mu would be more than the square deviation when calculated from x bar. So if we write this equation here, we divide it by n and take expectation, we'll get to the fact that in expectation, sigma square, so this term would reduce to sigma square, that is the population variance, is more than the sampled variance, and like this term actually would become xi minus mu divided by n, the whole square divided by n, and this term is going to be like xi minus x bar square divided by n, and this is nothing but the variance. And this is also, this is like deviation being calculated from the population mean, but in expectation it would be equal to the population variance. We'll skip the proof for now, but we can just assume it to be so. Now we can see that this is more than, so population variance in expectation is the population variance is more than the expected value of this. We can write it as expected value of this variance, sample variance. So if it is more, so if the average deviation when being divided by n is less than the population variance, what we can do is we can, instead of dividing it by n, we can divide it by a little smaller quantity, let's say n minus 1, so as to push the average a little higher, so that it can be a little bit more closer to the population variance. So if we see that if the population variance is given by this is the population size. If we calculate the variance by dividing it by n minus 1, we can think that it is slightly pushing it a little up. And how we can denote that? It can be denoted as the sample variance when dividing by n minus 1, that is here, as compared to calculating the sample variance when dividing it by simply n. Now, to keep things in mind for future references, we can also write the sum of square deviation as equal to this term multiplied by n minus 1, that is this, and that also can be equal to n times the sample variance when divided by n. So these two terms are actually equal and are equal to the sum of square deviations calculated by using the sampled mean. Now we can also observe the fact that if n grows, let's say if this is the population distribution and this was a small data set, this was a bigger data set, then this was a bigger sample data set. As n is growing, we are approaching the sample variance is kind of approaching or getting closer to the population variance, if we see so. So if let's say n becomes this huge number, n minus 1 would still be a very small adjustment, as the variance is already a good estimate, as in like it's already very much closer to the population variance. So that's why this is also a good correction to have now. But we are we know that, okay, we are just subtracting 1 from it, but why not n minus 2 or n minus 3 or maybe some n minus k? How should we identify that? How much should we be correcting? Should or how much are we off? Basically, we found out that, okay, this is more than this expectation of the sample variance is less than the population variance, but how much it is less than that? How off are we if we are dividing it by n? So to write it mathematically, we found that this is in expectation more than this. So let me. So this is the action. This is actually the expectation again. And now, if so, just to convert this inequality into inequality, we found that, okay, this has to be an offset, and let's call that offset a bias. Now, what is this bias? Can we quantify that somehow? So basically, we're trying to find the answer for by how much is the sample variance off when compared to the population variance, or how to find how much bias we can have in order to appropriately adjust it. Like, is the adjustment of n minus 1 sufficient enough or not? So let's take, for example, we have n minus 1, n just n equal to 1, that is, we are just considering one sample, and we have population mean to be mu, and we just take one sample. So the sample mean is going to be x1 again, and the standard and the deviation would also be 0 because we're just considering one sample. So if we just put in all these values into this equation, we found that, okay, the sample and if we just keep on repeating this experiment, like we always just are sampling just one sample, so it's always be the case that the mean would be that particular sample itself, and the variance is going to be 0. So in expectation, the variance is always going to be 0 for n is equal to 1, and the bias, if we see so, is like sigma square. So the variance is completely off by the whole population variance, if we see so. Now let's take, for example, n is equal to 2, so we just sample 2 points. The mean would be somewhere here. And similarly, in another experiment, we sample 2 points somewhere here, and again, we sample 2 points somewhere here. So if we'll observe that the mean would keep on shifting between the points. And similarly, we can just try to calculate the variance. But let's say, for example, let's say we calculate what is going to be the variance in this case for n is equal to 2, or let's say for n in general. But before moving on to that, let's just revise a few notations here. So expectation of x is given by mu, that is the mean. Expectation of x bar is also mu. X bar is the mean sample, and we discussed this earlier, that because this sample mean is an unbiased estimator, so this is going to be equal to the population mean, that is mu, where x bar is given by this formula, the summation of all the samples divided by n. Variance of x is sigma square. This is the population variance. And now, because we know for the fact that in this case, when we were sampling 2 points, the mean was somewhere here. Sometimes it was somewhere here. Sometimes it was somewhere here. Again, if we have, let's say, some n number of points, the mean would keep on shifting around. And therefore, we can say that there is also going to be some variance in the mean if we just keep on sampling again and again. So there could be some variance in the mean. How we can calculate that? So x bar is going to be this quantity that we are having it from here. And now let's see these equations. So variance of x plus y can be written as variance of x plus variance of y if we assume that these two are independent. And variance of x times x is also going to be like if a is a scalar, we can take a outside as a square, and it will become v of x, that is variance of x itself. So in this case, we'll take this 1 by n outside. This will become 1 by n square, and we can take the variance inside and the summation outside. So now this variance of xi is nothing but sigma square, and summation of sigma square, because this is independent of I, would become n times sigma square, and we get the variance of x bar to be sigma square by n. So if you see the variance, how much variance is there in the mean is dependent on the number of samples that we have. So we can also verify that with this example, where let's say if we have this population distribution, and if we are kind of having a sample set like this, and we are doing this sampling multiple number of times, keeping a very large sample size, we'll see that the mean is always going to be somewhere here, and it is going to be somewhere in this region itself. So the variance is going to be very small. So as n grows, the variance of x bar, that is the sample mean, is going to be reduced. Now let's come back to our example where we are trying to calculate the variance of n when we're calculating n number of points, when we're sampling n number of points. So let's say we are sampling these points. Let's say these are red points, and let's say for one particular point x1, we find the deviations from x bar and mu. So we see that this distance distance of x1 from mu is equal to distance of mu to x bar and x bar to x1. So we see that mu minus x1 is equal to mu minus x bar plus x bar minus x1. And if we just interchange the terms, take the square and expand the whole term, we'll get x bar minus x1 whole square, mu minus x bar whole square plus 2 x bar minus x1 mu minus x bar. Now this equation is just for x1. We can also do the same thing for x2, x3, x4, or any particular x of I. And let's say, for example, we just simply sum all of these up together. So now put just a summation here. So it will become summation of this term, summation of this term, summation of this term, and summation of this term all together. We are just exactly having the same term here. This I just interchange the positions because it's square. Now this term is independent of I, so we can take it outside, and this will become n times x bar minus mu. And for this term, this again is independent of I, we can take it outside. And for this particular term, this is actually but the deviation or the distance for all distance of all the samples from the mean. So what we're doing is, because mean is considered to be at the center of all the samples, this summation is going to cancel out all the terms, and it is going to be 0. So this term is going to be reduced to 0. So here, so we are just left with this summation that we are writing somewhere here. And now if we take expectation on both sides, so we are going to have this term, this term, and this term here. And this, if we multiply and divide by n, this is nothing but sigma square in expectation. That's what we got it earlier. This is nothing but the deviation of all the samples from mu. So, and in expectation, it is going to be becoming sigma square. This is also, we found that if we are calculating the square deviation from the sample mean, it can be written as n times Sn square. And this term is copied as is. So now we can just simply cancel out all the n's here. So we get sigma square, we get expectation of this variance, sample variance. And this term, if you see, this is expectation of square deviation of x bar from mu. Mu is nothing but expectation of x bar again. So we can see that we are calculating the expectation of something, that is expectation of the square deviation of something from the mean of that particular entity. That is again nothing but the variance of x bar. So we also calculated that the variance of x bar is nothing but sigma square by n in expectation. So we found that the population variance is equal to the expected sample variance and plus the variance of x. And so this is the bias that we had earlier. So this is the offset. Now another way of actually doing or solving this equation would be to, instead of replacing this term by n times Sn square, we can replace it by n minus 1 Sn minus 1 square. So this whole term would reduce to n times the variance of x. That is fine. And that would become, and then if we keep on solving that, we'll get to the fact that the population variance is equal to the expectation or expected value of Sn minus 1 square. So there is no offset here. The bias is 0. So and we discussed in the earlier videos that if in expectation the estimator is equal to the population parameter, it is an unbiased estimator. So now we got to know that in expectation, if we divide the deviation by n minus 1, it becomes an unbiased estimator of the variance. So and if instead of the fact that if we divide it by n, we do have an offset of the variance of x bar. What could be some other ways of inferring this equation? So the equation says that if the population variance is equal to the expected value of the sample variance plus the variance that is there in x bar, so it can mean that a part of the true variance, that is the population variance, is captured by the fact that the sample mean itself wiggles around mu, and that we have already observed that if we are just in this case, if we are having a population variance here, population distribution here, and if we are just keep on having different sample sets, the mean is going to be moving around here and there, and there could be and there is a variance that can be captured by the sample mean itself. So and if we are measuring the deviations from the sample mean instead of mu, we lose that amount of wiggle that is there. We can see from this example, as in these are the point, these are the same distribution that I've just simply copied here. And if, let's say, consider this is the sample mean, and if we calculate the deviations from the sample mean and the variance in this case and the variance is in this case is exactly going to be the same, because there is no change in terms of the deviations that are going to be there and the number of samples that are going to be there. But if we calculate the deviations for this distribution from the population mean, and again for this distribution from the population mean, the variance in this case and in this case are going to be different. So it means that we lose some information if we calculate the variance using the sample mean and not using the population mean. But we anyways don't know what is the population mean. So basically there is some information that is anyways going to be lost if we are using the sample mean. And and that because of the fact that the sample mean can have a good amount of variance, or the variance depends upon the size of the sample set. And in order to make it unbiased, instead of calculating or dividing it by n, we can divide it by n minus 1. So n minus 1 is a statistical proof why we use that instead of any estimator like n minus 2 or n minus 3. We can, and in some cases we can use n minus 1, n minus 3, sorry, n minus 2, n minus 3, or some n minus k, depending upon our requirements. If we want to overshoot the variance, or if we want to overestimate the variance, there could be several other requirements, but those are still going to be biased estimators. So only n minus 1 is the unbiased estimator. N minus 1 as in, like, if you divide the deviation from n minus 1 by n minus 1. So yeah. Uh, so what we have looked into so far is the population variance given by sigma square is given by the expected square deviation of the samples from the population mean, and this actually is the true spread of the distribution. Sample variance, if calculated by dividing the deviations by n, and deviations being calculated of using the sample mean, is a biased estimate, and it underestimates the true spread, that is the true variance or the population variance. Sample variance, when calculated by using the sample deviations using the sample mean and dividing by n minus 1, is an unbiased estimate, and the bias in the case where we divide by n is given by the variance, or is captured by the variance in the sample mean, and is given by sigma square by n. And as n increases, this variance of x bar also reduces, and the sample variance get closer and closer to the population variance. And this is the missing spread that was because of which the sample variance in this case becomes an underestimate. So yeah, this is it for this video. In the next video, we'll try to understand the difference between variance and entropy. Both actually are some measure of capturing spread in a distribution. So yeah, we'll see you in the next video. Till then, happy learning. Thank you.